This is a little addendum to the leaf level control of transpiration material to get into the weeds a little bit regarding the mathematical relationship among the different resistances, the component resistances that make up the leaf resistance term. So if you recall, I mentioned earlier that leaf resistance term is a function, and I used that on purpose, a function of the boundary layer resistance, the stomatal resistance, and the cuticular resistance that show up on this diagram. And I used that notation explicitly because it's not a straightforward arithmetic sum of those three resistances. And that's because we can't add up those three resistances in an arithmetic form because of the nature of how the mathematics of this circuit analogy work. So I'm going to talk about that briefly here. So backing up a little bit, what we're dealing with those three component resistances in a leaf is we're dealing with resistances both in series and in parallel. So these are diagrams showing resistances either in series or in parallel, where the current or the flux flows through those resistances either one after another, as in the series case, or individually and separately, as in the parallel case. And in circuit mathematics, resistances that are in series are additive, while when resistances are in parallel, you have to add those as conductances. They're inverse. So the mathematics works out so that you can directly add or arithmetically add resistances in series, but when you add resistances that are in parallel, you have to add them as a conductance. So then in moving from our electrical diagram back to the leaf diagram, translating that, what that means is that the stomatal resistance and the cuticular resistance are resistances in parallel, while the boundary layer resistance relative to both the cuticular and stomatal resistance is in series. Because if you think about, for instance, the movement of a water molecule, which is what we're concerned about here, water molecules would have to move in parallel if they're encountering either cuticular or stomatal resistances. Those two resistances are in parallel. But if a water molecule has moved through either the cuticle pathway or the stomatal pathway, they then have to move through the boundary layer resistance. So that makes that boundary layer resistance in series to the other two. So that then conditions the math that we need to do to formulate the leaf resistance from its component resistances. Mathematically then, to get leaf resistance from those component resistances, first we need to get the sum of these resistances, which are in parallel to each other. Since those are in parallel, those have to be added as conductances. And remember, a conductance is just an inverse resistance. So to add those, we add them as conductance, which is just 1 over stomatal resistance plus 1 over cuticular resistance. So that's a conductance. That's a conductance. Okay. But then we want it to convert that back. That's then some conductance of those two, both cuticular and stomatal components. So because we're then going to add them to the series resistance of boundary layer resistance, we need to turn this back into a resistance. So we then inverse that summed conductance and turn it back into a resistance. So this then ends up being the formulation for the calculation of the total leaf resistance. Why should you care about this? It's unusual for any of us to, for instance, measure individual resistances as components, although we might occasionally. Certainly in my graduate work, I did some independent measures of boundary layer resistance in leaves, for instance. But I think in most modern physiology, the reason that it's still important to understand this kind of mathematics is because any gas exchange system that you're using contains calculations like this. And you need to understand how this stuff works. And if you, for instance, dig into your Lycor LI 6800 manual, in the technical parts, these types of equations will be there. Now, they likely don't have a cuticular resistance or conductance in there because it's usually assumed to be impermeable. But I can guarantee you they do, for instance, the series or parallel sum where it's appropriate of these other resistances. So I think it's helpful to understand how that all works and to be at least familiar with how those types of calculations happen.